All right, welcome to week 7, Thursday 8 a.m. section. As a reminder, I am Jax. That is my email there in yellow. If you guys have any questions or like general concerns, I've already gotten a couple of students that are a little bit worried about where they are in 15A. Send me an email. I am very down to help. And that also goes for other students that might be watching the section video that are not from my section. I'm here to help. So reminders first. Quiz 1 grades are out. You can find those on Gaucho Space. I do highly recommend that you take some time, like 15 minutes at least, and like look through the quiz 1 and where you struggled, where you did well. It's always good to point out what you do well when it comes to classes. But I think I already went over last week. Quiz 1 was difficult. And I'm assuming after that midterm you guys just took this week, 15A problems are difficult in general, so it helps to review them. So check those out. You are welcome to request regrades, except I did do my best as I could on partial credit. But any questions about quiz 1 and also like the solutions, if you don't understand them, I did send those out to you guys last week. Feel free to send me an email. Another thing, logistically, you guys get a break Monday. You have no class because it is President's Day. So please do not show up to the lecture on Monday. It is a holiday. So catch up on work, rest. I don't know, go to the beach, do something nice for yourself. You deserve it. And the final reminder, homework 3, I hope you guys have been making your way through that. Try not to leave it the last minute, but you know what? If I held that to you guys, I'd be hypocritical because I'm also a procrastinator. That's it for reminders. On the agenda, we just went through reminders. We're going to talk about the midterm, not in depth. I don't have time for that. And then we're going to go over 2 things, multi-level logic and gates, which are very much intertwined. So midterm postgame. First off, when Professor Zhang showed the TAs the midterm, so we could like look it over really quick before you guys took it, I was even it took me a minute to understand a lot of the questions. And so that being said, if you felt like a really hard part of that midterm was figuring out what the question was asking, you're not alone. It wasn't easy. It wasn't trivial. And I don't know how you guys done the midterm. I wasn't at the midterm proctoring it. But just from looking at the midterm questions, they're kind of big brain questions. They kind of really make you think. And so not only did you have to apply what you've been learning from the homeworks, from these sections, and in general in 15A, you kind of had to think about how does that apply to problems that you haven't seen before. And so don't worry if you feel like you took an L on that midterm. I think, God, I've taken a number of L's my sophomore year, and that was mostly due to the 10 series, but 15A is not an easy class. It is required. One thing I really do recommend, kind of like what I suggested with the quiz, once he comes out with the solutions and you guys get your grade back, you should look over how you did on the midterm. Where did you struggle? And where can you improve in general? And so I know it's really like we don't want to look at our mistakes. I am guilty of this where I don't even want to think about the midterm, but you should. It's good to know how you're doing in a class. And also it's good to then improve so that you do better on the final. So that being said, dudes, don't dwell on it. If you didn't do so hot, it's recoverable. And you got other stuff on the horizon. I know you got other classes, you got other assignments. So if you took an L, you took an L, put it to rest. Don't let it stress you out, okay? So I'm very proud of you regardless of getting through that midterm. Now, let's move on to learning about what today's section is covering, gates. So I have listed out 5 gates that you should have seen before. We have an inverter, a buffer, an AND gate, OR gate, and an XOR gate. And you should remember that XOR gate from one of your homeworks. So if you remember, an inverter symbolically looks like this. And what it does, it takes a single input and on the output, it inverts whatever that input is. And so you can see by the truth table here, if A is low, the output is high. And if A is high or equal to 1, its output is low. That is a basic inverter. Now, even easier than an inverter is what we call a buffer. All a buffer is you can think of it as a repeater. It simply takes the input and spits it out on the output. There's no change, absolutely. And so if the input is low, so is the output. And if the input is high, it is also high on the output. Those are our easiest gates, and they're symbols that are not technically a gate, but they are a circuit symbol that you guys should be familiar with. Now, a little bit more complicated are two input gates, like AND gate, OR gate, and XOR gates. So for an AND gate, if you guys remember, this is what it looks like. Oh, that I'm on the eraser mode. That's not really helpful. This is what an AND gate looks like. In Boolean algebra, it's multiplication. So that could be a dot, that could be a little asterisk. I've seen people do X's. All of these mean multiplication and also ANDing in Boolean logic. And its truth table looks like this, where it is only high when both inputs are high. So moving on, we have an OR gate, which its associated operation, at least in Boolean logic, is addition. I'll center that. And there's only one way to really represent OR gates. With addition or logically, this is what an OR gate is. Also an AND gate in logic, you can think of an ampersand sign. But kind of opposite the AND gate truth table, any input combination where A or B is equal to 1, you're going to get an output that is high or also equal to 1. The only case in which an output is low is when both of the inputs to an OR gate are low. So let's look at AND gate and OR gate truth tables. You can see that I like to think of the AND gate as kind of it's a little picky as far as when it comes to what input combinations give you an output value of a high. 1 and 4, and by 4, I mean that there's 1, 2, 3, 4 different input combinations in a 2-input AND gate. 1 in 4 chances of getting an output that is high. Now the OR gate, it's not picky. It's kind of a people pleaser. It's really easygoing because any input that is high will give you an output that is high in an OR gate. So you have 3 in 4 chances of your output being high when you have a 2-input OR gate. All right, and we should remember that. Now the one gate that we saw, I think it was homework 1, is the XOR gate, and that's represented by the symbol here. And XOR stands for exclusive OR. So that means in the truth table, only when A and B's are exact opposites of each other should the output of this XOR gate be high. And that is why when A is low, in order for the output of this XOR gate to be high, B needs to be high. So 1 is opposite, go and compare it to 0. Same thing for if we wanted A to be high, the additional input would have to be low in order for our XOR gate to give us an output that is also high. In any other cases where the inputs are the same, so either they're both low or they're both high, we're going to get outputs that are equal to 0. And this is for an XOR gate. All right, so these are all gates symbolically, and also just like in Boolean simplification, you should be familiar with. If you're not, come talk to me. New kids on the block. NAND gates, NOR gates, XNOR gates. These guys are not that hard, but they are frequently used in industry. And that's because, at least for NAND gate and NOR gates, you can change any Boolean expression solely using NAND gates or solely using NOR gates. Whereas in other Boolean expressions that you guys have been working with have been made with both AND gates and OR gates. So NAND and NOR are very powerful, and they're also very popular. So NAND gate is simply an AND gate with an inverter attached onto the output. So if you remember, our AND gate output truth table for a 2-input AND gate looks something like 0, 0, 0, 1, right? And if you attach an inverter, you're going to change anything that's low to high. And this final high, where both inputs A and B are equal to 1, is going to now be low in our NAND gate truth table. So you would fill this out like this. All right, keep in mind, this NAND gate truth table, this NAND gate operation is not the same as OR, even though you associate both of them as opposite of an AND gate. Let me just sanity check you and make you understand that, because this output 1 1 1 0, right? Just going down the list. Here, the output of an OR gate is 0 1 1 1. Yep, that's all I meant. I'm not going to say anything after that because it's a 2-input OR gate. 1 0 and then 3 1s. Here in a NAND gate, you have also 0 1 0 and 3 1s, except for different input combinations. So NAND is not the same as OR, and it's definitely not the same as AND, because it stands for not AND. That's what the N in front of NAND, or in front of the N in the first N in NAND stands for. Moving on, let's chat about NOR gates. Very similar. So the truth table for an OR gate is 0 and then 3 1s, right? That's the output for a 2-input OR gate. And now if we invert it, we're going to get a truth table that looks like 1 0 0 0. All right. So NOR stands for not OR. So anytime an OR gate would be high, it would be set low in a NOR gate. And anytime a output would be low in an OR gate, it would be high in an OR gate. All right. I know I'm going to say AND, OR, NAND, NOR a lot. You got to differentiate between them. And last but not least, we have an XNOR gate. And it's not an XOR just because it's easier to say XNOR, but it stands for not exclusive OR. And if you remember, for an exclusive OR truth table, the outputs look like this. And so when we invert it, it looks something like 1 0 0 1. And as you can see, if both the inputs are the same, they're going to have an output of high. Whereas if they're different or exclusively not the same, they're going to have an output of 0. And this is for an XNOR gate. All right. And symbolically, these are nothing different than their corresponding non-inverted gates, except you have this little bubble here on the output of your gate, which is the exact same thing as simply attaching an inverter to the output of your gates. All right. So we just went over all of these gates and their truth tables. And these are really, really powerful symbolic representations that can represent certain operations in our functions that we're expressing in Boolean algebra. And gates in the real world are represented with, or not represented, they physically are transistors. And you'll be getting into that more so if you're in EE, and also you should be in your 10 series. So now, we know what all these gates are, what they mean, what they do. Multi-level logic. You can see I have a circuit here, right, that has a bunch of gates. Looks like we got an OR gate here, we got AND gates here, we got an, oh, that's not a symbol for an AND. We got AND gates, I'll do multiplications. We got an OR gate here, AND gate. It alternates, right, between ANDs and ORs. And this shouldn't be too unfamiliar to you, because when you guys write out your function expressions, either in product of sum form or sum of product form, you alternate between using OR gates or addition symbols and AND gates, multiplication. And so what I'm going to show you is what each of these circuits translate to in Boolean algebra. And so as you can see, this is a multi-level logic circuit because there's these 5 stages here, level 1 through 5, level 1 being closest to the output. That's what this F1 means. Let me just denote that, saying that this is the output, this guy right here. And that's our function, right? And so starting at the innermost term is over here in level 5, where you have an OR between D and E naught. All right, that's what level 5 is simply doing. And then next, in level 4, I'm going to go below, we take the output from this D plus E naught and we feed it into an AND gate, where we multiply in variable C. And then also going on in this level, this is level 4, we have the multiplication between F naught and G naught. All right, so that is what is going on in this level 4 as far as what product terms are being calculated. Now, these product terms are feeding in to this OR gate in level 3. All right, so I'm going to copy these terms and we're going to move up to the top because I'm running out of space. And all an OR gate is is putting an and symbol, right, between these terms, except we introduce a new variable in this level. And that variable is b not, all right? So b not is introduced in this third level. And so far, this expression that I highlight in yellow covers levels 3, 4, and 5, all right? Now, this whole expression is going to feed into an AND gate in level 2. So we take that entire sum, you can call it, and it's going to be ANDed with a not, right? Because that's where it's coming in here. So let me just keep the color coordination correct. But I'm ANDing that entire expression with a not. That is a highlighter, so that's not particularly useful to us. A not, and then also there's another product term going on, this h multiplied by I naught multiplied by j naught. And so let's ignore that. I don't know if we'll run out of juice, but hopefully I'll make it in time. We have this h multiplied by I naught multiplied by j naught also going on in this part of the circuit. And this is level 2 of our circuit. Now, last but not least, we take both of these product terms that we calculated, or we determined, not necessarily calculated here, and those are going to be feeding into a final OR gate along with the lastly introduced variable k. And so I am going to copy all these guys that we just created. And we are going to be, I'm just going to get rid of these guys. They're kind of redundant because multiplication, you can just put variables next to each other. All I'm introducing in this final part of the circuit is the variable k. And I will make all other terms black so that you can see that only the variable k was introduced in level 1 of our circuit. And we have no more circuits, symbols or elements to translate. And so we've reached the final Boolean expression of the function that we just translated from this circuit diagram, and it is equal to F1, right? Because that's what the output is called here. F1, F1. F1 is equal to all that good stuff. So as you can remember, we started at level 5, and then we piled on that output going into level 4, which was here. And then we took both of those outputs that we calculated in level 4, fed them into an OR gate in level 3. And then that eventually gives us a final expression that, when written out nicely, is this F1 equals expression here, where you can see which terms or variables were introduced at which levels of our circuit diagram. So these are equivalent. One just has all the colors. So that was really cool. We just translated a circuit into Boolean algebra expression where the gates are reflected in the operations that we see in between variables. Now, I'm going to do a cool thing where I take this expression here and I'm going to change it such that we only use NAND gates, because you can change any expression that uses AND gates and OR gates to an expression that fully uses NAND gates or fully uses NOR gates, and they remain equivalent. How do we do that? So I have the expression written nice and neat here. And what you remember from a NAND gate is just ANDing with this inversion symbol around it, right? So we're going to be playing a little bit of De Morgan's game, where we're going to be taking out complements and putting them back in order to get rid of all these OR gates. We want to get rid of every single one of them, and we're going to do that with layered NAND operations. All right, so let's start. We want our outermost level to be a NAND gate, and so we are going to take out a complement. All right, and that's going to look something like this. And I'm going to copy my expression, but every time I see an OR, I'm going to replace it with an ANDing. So I'll just do that. And then each of the terms that were split by ORs are now going to be, I'm going to use another color, inverted, right? So this A term, this K term, and this HI term, HI not J term are all going to be inverted, if you remember from doing De Morgan's law. So already we have an outermost NAND gate represented by the square brackets in red and the complement term that is on the right of it. And we also have a successful NAND gate here in blue that covers H, I naught, J. And so we don't have to touch anything over here because all we see is multiplication. But I see OR gates here and we want to get rid of them. So we do the same process again. All right, bear with me. And it's going to get a little complicated as far as parentheses and colors. But I think you guys will find it useful for understanding it afterwards. So in order to pull out a complement from these square brackets here, I'll denote them in, let's do purple. And this entire term that is encapsulated by a square purple bracket, that is being multiplied by this A naught term. So do not forget that. But that means that I can basically get rid of these OR gates that are in between my terms, turn them into AND gates, and then each of my terms need to be inverted, right? So that means that this entire thing is inverted. I want to make sure that it's very clear. There's a multiplication symbol there. This B naught is inverted. There's double negation there. And this F naught G naught term is also inverted. All right. So we can clean this up a bit and see that we have B double naught just turns to B. I'm going to try and make that very clear that that's supposed to be ANDing. We have a successful NAND set up here because all we see is multiplication surrounded by parentheses that have a complement on the edge. And the final OR gate that we have to get rid of is this one here. Let's use orange to denote. Is this one here. And that is nothing more. I'm going to make this outer one a different color so you guys can like not get crazy confused. We'll make it pink. So we can do our final step where we get our NAND gate, and that we invert this term here, and I'll outline the OR term in orange, and we are going to pull out a complement. Let's move things over to give ourselves some room, and this OR gate now becomes an and we invert its terms. So D becomes D naught, and E naught simply becomes E. Alrighty, let's take a look at our expression. We see no addition symbols, and it looks like there's complements on every single set of parentheses around all of our terms. And that means that we have a successful NAND gate circuit. So to remind you, what we just did is we took this expression up here that solely used AND gates and OR gates, and we turned it into an expression where all you need are NAND gates. And so what does this expression look like when we translate it to a circuit realization? Let's do that up here. So for my iPad users, this is equal to F1. I really recommend that my iPad users make a sticker or they have circuit symbols off to the side. It really speeds up drawing your circuitry realizations. To my people that like pen and pencil or pencil and paper, you really should not do your homework in pen, but I had a friend that did that in 15A and he was kind of chaotic. Anyways, you guys should really try and be neat when it comes down to making your circuits, because it makes grading a lot easier, and it also means that we don't have to guess if that's an AND gate or an OR gate in your guys' circuits, because there's one thing we hate more. There's nothing we hate more as TAs than not understanding how to grade your guys' stuff. So I will build this circuit from the inside this term here. If you remember, you can kind of associate this D and this E variable with level 5 over here when we had its AND OR realization. But since we're working in NAND, we're going to be using NAND gates. We can start with our innermost NAND gate term here, and I will try and keep things color coordinated so you guys can see in the function which NAND gate it corresponds to. We introduce the variables D naught and E. All right, and that is being multiplied by C in the next level. And so that output will line up with this input, and the input of, oh, apologies, this should be a purple parenthesis. All right, now the world makes sense. Thus, this NAND gate, which is taking the output from level 5 and the input and multiplying it with C, is represented there. And then if you continue going, that is fed into the next level, in which we have actually 3 inputs. And this is the pink outermost square brackets you can see in the original function, where we are taking the output from our purple AND gate or NAND gate, multiplying it by B, and then also we have to go back a level in order to account for this F prime G prime term. So that is going to be in this level 4 here, where we have F prime multiplied by G prime or ANDed together, and that is all done under the roof of an AND gate. And so this then feeds into our 3 input NAND gate represented in pink. And then that is going to be multiplied by, if you guys can see, I'll try and keep things relatively clear, this A0 term here under this blue NAND gate. So that looks like this, where this is feeding into a circuit and we have A0 being multiplied in, and this is a blue NAND gate representing kind of like the heftiest, I think, part of the circuit. You know, we gotta wait for a lot of inputs to trickle in order to get to this point. So that's what I mean by hefty. And that is going to be multiplied by K0 here, and also another blue NAND gate, which we can take care of really quickly. That multiplies in 3 terms. So we have 3 inputs to this NAND gate, and that's going to be H I0 J. Has to be blue because that is what it's symbolized in our original function. And then these 2 terms that come out of these 2 blue NAND gates are going to be multiplied by that K prime term, this one right here, all under our outermost NAND gate, which is denoted in red in our F1 expression. So we are super close, but basically this feeds into 1 input of our NAND gates. We also have K prime, which I like to put my extra variables being introduced in a new level in the middle, just because it keeps things cleaner. And then last but not least, this attaches to my final input of my outermost NAND gate of my circuit. And I don't have enough room to write even F1. So we're going to shift things over. And we've now run out of variables. And that is the output of our final circuit. And so as you guys can see, we have translated an original expression that was solely AND gates and OR gates, and its circuit looked like this. Sorry if I'm moving the screen around a lot. And then we took that AND and OR expression, we turned it into an expression that solely used NAND gates in order to mean the same thing. And then we took that NAND expression of F1 and we translate it into a circuit that, as you can see, solely uses NAND gates. If it's still difficult for you guys to follow along how this expression kind of translates to this whole circuit looking thing, I recommend looking through my notes and trying to follow the color schema yourself, because it takes some time to do this with a little bit of an intuition, because it's not easy trying to translate what we were familiar with as math into stuff that's looking a little bit more like circuits. All right, so all that's hiding under this box, I'm pretty sure, is if I'm right or not. And it looks like, after double checking my work, I have made no mistakes. But trust me, doesn't mean I don't make them at other times. So let me check on time. We're doing not bad, but I have a final exercise that kind of like talks about gate circuit realization, where we have an expression of min terms, a crazy amount of min terms, and we have 5 variables, and we want to find a minimum 2-level NOR gate circuit to realize F. So NOR gates. If you remember, NOR gate has the look and feel of this, where we have or in between each of our individual terms, and then we have a final complement on the outside. But we need an expression first. And there's multiple ways you can find an expression for F, but I think there's still some slight confusion with how to do K-maps, especially 5-variable K-maps. So let's use a K-map in order to understand how we are going to create a 2-level NOR gate circuit of this function F. So first off, let's fill in the midterms. As you can see, this 4x4 is going to represent all of A is equal to 0. And then this 4x4 is going to represent all of A equals 1. And then B, C, D, E, the variables following after A, are represented by the normal headers that you see in a regular 4x4 K-map. So midterm 2, 0, 1, 2, and midterm 3 are both high. Then we have 6 and 12. So that's going to be 1, 2, or 0, 1, 2, 3, 4, 5, 6. 12 is going to be 8, 9, 10, 11, 12, 13, 14, 15. So we are out of this first 4x4 K-map because this accounts for the midterms 0 through 15, and this one accounts for the midterms 16 through 31, if you guys remember. But moving on, we have 16, which is this slot right here, 17, 18, 19. I will cross off my midterms once I call them out. And then we have 20, 21, 22, and then we have 23. So that means this is 24, 25, 24, 25, 27. And then last but not least, we have 28, 29. This is 30, and this is 31. So we have covered all of our midterms. Lovely. Now, I am just going to, for the sake of completing all of this, fill in the rest of our K-maps with zeros. And I'm not just doing this for grins, but I want to find a minimum product of sum for F, and you'll find out why later. But that means that I'm going to find a sum of product for F naught, and that means grouping zeros. So first thing I'm going to do is look and see, okay, clearly I got to work with this K-map first and find as large of groupings as possible in order to find a minimum product of sum for F, or a minimum sum of product for F prime. So I'm just going to start boxing as I normally would. You can kind of imagine these two 4x4s on top of each other, and that is why that you can group these four max terms, because they're zeros, together. And let's see, we also want to take care of these guys, and the only ways to do that is by, well, first off, changing this color to something that makes a little bit more sense. And since this is, oh, didn't mean to do that. And this is on top of A1, you can kind of think of it as stacked as on top of A0. That means it's also going to group those other two zeros on the A equals 0 K-map. And then finally, I'm going to capture these max terms with an orange vertical box, and we play the same game. Okay, lovely. So now I want to keep on going. Looks like I can group 4 solely on this A equals 0 K-map because this one's already complete. I want to do this grouping and this grouping because they're left over, and that's the largest grouping I can do in order to capture these zeros that have yet to have a buddy. And then that means that what's left is these two zeros, and I can encapsulate them in the largest grouping possible, which is 4 squares together. If I did this, this would be an accurate reduction for F, but it wouldn't be the most minimal because this is an implicant, but this is a prime implicant. So now that we have our K-map denoted, I am going to show you how this translates to F prime. And keep in mind that we just box things and it's going to give us the sum of product for F prime. All right, if we inverted this entire K-map such that all the zeros were ones and all the ones were zeros, that would be the K-map for F prime, right? That's why we're doing this in the first place. And so I'm going to try and show you what each of these terms are. This pink term, let's start on A equals 0, is going to be A naught because A is equal to 0. And then the thing that is most in common is C naught, and then also D naught here. So this first term is represented by the pink box in our expression. Let's see, the purple box, that is going to be A naught as well as B, which is set high, and then also D is set high. So this is A naught BD in our expression, which is this term here. Let's see, our red box, which covers A naught and not A naught, A is equal to 0 and A is equal to 1. That means that A is going to be our expression for this term. So what it is B, because B is high in both of these columns, and also D E naught, which is this term here. Moving on, I'm showing you that this orange term here is B naught C, and then also E, because E is set high, and that is this term here. And last but not least, we could double check it. Also B naught C, except in these two rows, D is the D naught is the thing that is in common. And so that's why the green square on our K-map represents B naught C D naught. All right, lovely. We found F prime, but what we want is the product of some form of F. And I promise you, I'm going to explain why this translates to getting a NOR circuit. But if you remember, all how you get a product of some form for F is by applying the complement, because F is equal to F prime prime, right? So if you apply the complement, all of these terms are going to turn into their complementary OR gate expressions. So this is going to be A plus C plus D, and it's going to be multiplied by B plus C naught plus D, and that will be multiplied by B plus C naught plus E naught. And we have a purple term that is A plus B naught plus D naught. And last but not least, we have a product term that becomes a sum term of B naught plus D naught plus E. All right, that is our product of sum. Now, we have a product of sum expression for F, but we want an OR gate expression. And so, like step 2 says, we're going to NOR gateify what we just found for F. And all that is taking out a complement. All right, what does that look like? I am going to show you that if I take out a complement of this product of sum expression, all the AND gates become, I'm gonna need to give myself a little bit more space. All the AND gates become OR gates, right? And all of our terms get negated. And since all of our terms are already split with addition symbols or OR gates, the work here is done, guys. We have successfully NOR gatified our original expression, which was just a bunch of min terms. This guy, which I unfortunately crossed out, so who knows if you can see that. But how does this translate to what the question originally asked, which was for a 2-level NOR gate circuit to realize F? Well, you can see that we have 1 level here, our outermost NOR gate, which takes in 1, 2, 3, 4, 5 inputs. And then we have 5 smaller NOR gates, which take in 1, 2, 3 inputs. So that looks like the following. We have 1 level of F, which takes in 5 inputs. So I'm going to add 2 more inputs onto this 3. And then we have, in order to account for each of those 5 inputs, 5 more NOR gates that have 3 inputs each. So I'm going to copy and paste 5 of these NOR gates, and I'll assign their inputs accordingly. All right, I think that looks good. So let's just attach our 2 levels first off, and I'll have it make a little bit more sense to you guys. One pro tip when you're doing circuits and you want to keep things neat, space things out. You guys have space, you should definitely use it. Oh, I just wrote 4 inputs. Silly. Let's make some more room for this guy coming in hot. This guy is going to be on the outermost turn. And so this guy should back up. All right. Take space. I think we like to cram things because we are very concerned about saving paper, which is good. But the one thing you really should not cram are your gate realizations. You should take your time with them. Low key, if you're an artsy person, get into the colors. If you're not an artsy person, just try. And I say, please try to keep things neat. So we have kind of like the structure, and we're going to start assigning inputs based on our expression that we realized over here. So actually, let's just go back and forth. If you see this OR gate here, we have A, C, and D going into a NOR gate. My bad, I said OR gate. That is going to be here. So that would be A, C, D coming in as inputs. And then we have this green NOR gate here, which is B, C, not D. So we have B, C, not D going into that second NOR gate. And this orange NOR gate expression is B, C, not E, not. B, C, not E, not. And these are all being summed together in an OR gate and then complemented, which is why it's a NOR gate. And this purple term, A, B, not, D, not. A, B, not, D, not. Last but not least, we have our red term, which is B, not, D, not, E. B, not, D, not, E. So what have we just done? We have changed this entire minterm expression using K-maps into a, let me have my red here, minimum product of sum expression for F, which is here. And then we changed that product of sum expression into an expression that solely uses NOR gates by just taking out a complement. Simple as that. And then we finally drew the 2-level gate realization, 1 level, 2 level, for that expression that we just found, solely using NOR gates. So pretty cool stuff. It takes practice getting used to looking at an expression and then kind of seeing how it will translate to a circuit. But I highly recommend you put in the time and practice to understand that, because in your next required classes, you're going to keep on doing the same thing. So you better be somewhat decent at it by the end of 15A. As always, if you have any questions, send me an email. Other than that, I hope you guys have a safe rest of your week. All right, ciao.